Unit 2.21B. We're working with polynomial identities, continuing on with that. And at this point, we want to start feeling more comfortable with the method of proof. So if I ask you to prove something, or if anyone walking down the street asks you to prove something, we want to feel comfortable that we could prove it not just for some special case or some specific situation, but in general, so that no matter what, we can say, you know what, this works no matter what. And so let's just kind of review. Okay, so let's say you're walking in the street and someone comes by and says, hey, I want you to prove the following. There, see these two objects? I want you to prove that the area of the red one is equal to the area of the blue one. Okay. So think for a second. How would you do that? How would you prove that the area of the red box is the same as the area of the blue box? Pause. Think about it. Well, one of the ways you could do it is you could say, okay, let me find the length of this side, multiply them together. I'll get some number. Then let me multiply the length of this side with the length of this side, and I'll get a number. And if those two numbers are equal, well, then the areas are equal. If they're not equal, then the areas are not equal. And what we're getting at is that to prove something, you have to show that whatever it is on the left is exactly the same as the thing on the right. Okay, so if I'm asked to prove the areas, this is, the area, this number is the area of this shape, and this number is the area of this shape. I want to show that those two things are equal. Now, I want you to also think of it in a slightly different way. Imagine that these two objects were made out of silly putty, okay? And what you could do then is you could say, okay, let me take this object over here and let me do a few things with it, okay? Let me change it around a little bit. So you mess around with it a little bit, and what you come up with on the right side is something that looks like this. Okay? And then you look at the right side and you say, okay, something that looks like this. And you actually hold them right up next to each other. One completely, just perfectly overlaps the other. There's no overlapping whatsoever. There's no, one isn't slightly bigger in any area than the other. And so you say, hey, look, they take up the exact same amount of space. Okay? And this is kind of what we're getting at. When we are proving something, some polynomial is equal to some other expression, what we've got to do is we've got to change one of the sides so that it looks just like the other side. Okay, so sometimes maybe it's easier to change this one. Maybe the blue material is a little easier to move around and the red material is not. So we move the blue material and we try and make it look just like the red material. And what we're really getting at is that this idea, the concept that we can compare quantities. So if I can represent the area of this in a number, and I can represent the area of the red shape in a number, I want to show that those two numbers are equal. Okay? And essentially what I'm doing there is I am manipulating one of the shapes so that it looks just like the other shape to convince myself that they're the same thing. And so we want to take this idea, and when we are asked to prove something, so I'm just going to write something totally random. So if you're asked to prove that a plus b squared is equal to a squared plus 2 times a times b plus b squared, well, maybe you believe me, maybe you don't, but what will you have to do to show that these two things are equal? You'll either want to take this piece here and make it look just like the left side, or you want to take the left side and change it around so it looks just like the right side. And in this case, we know how to FOIL, so a plus b times a plus b is something that we can rewrite. We keep the right side the same, and then when we FOIL, we see that we get a squared plus 2ab plus b squared, which is exactly the same thing as we had on the right. Okay, and so keeping this idea in mind will allow us to work with some more difficult situations. So on the next page, I have a couple of, or maybe just one problem for you to try and really work on. All right, so here we go. So we want to prove that for any numbers x and a, the following identity holds, and that is that x to the n minus a to the n is equivalent to x minus a times the quantity x to the n minus 1 plus a times x to the n minus 2 plus a squared times x to the n minus 3 plus a cubed times x to the n minus 4, so on and so on and so on, all the way until you get a to the n minus 2 times x, and then finally kind of reverses cycle, so you have a to the n minus 1 plus a to the n minus 1. Okay, and this is a lot just to start off with, right? It's a big identity, a lot going on, and so to help you out, I'm going to suggest that you start with something a little bit easier. So here we're dealing where n could be any number, okay? Why don't you just try showing that this is true when when n is 3. Okay, so if you had x cubed minus a cubed, you want to show that that would equal x minus a times, well, x to the n minus 1, so n is 3, so n minus 1 is 2, okay, x squared, plus a, now x to the n minus 2, so n minus 2, 3 minus 2 is 1, okay, so we're fine there, plus, okay, now we're on the second one, so a squared, right here, I'm just following along, so a squared times x to the n minus 3. Well, what's n minus 3? What's 3 minus 3? It's 0, so x to the 0, which is just 1. And so I have a squared times 1, and we want to show that that's true. Okay, now this is a lot easier. It can kind of help you wrap your mind around what you're going to want to do here. Okay, so in looking at this, what I want you to do right now is pause the video and just write down what it is that you need to do in order to prove this identity. Okay, and then once you've done that, go ahead and try it out. Try working it out in this situation here, and then when you feel confident about that, go ahead and try and see if you can implement the same strategy to prove the one where n could be anything. Okay? And then at the end, I'll just say a few things and we'll talk about it more in class. Okay, so I hope that went well. I just want to talk briefly about how you might work with the example that we have here when n was 3. And if we look, we're trying to make the left side and the right side the same. And maybe you fiddled around with the left side, but it's really easiest to work with the right side. And I want to give you an example that will help you figure out how to simplify the right side. So if I have, let's take a look here. Let's just say I have x minus y, and I want to multiply it by a plus b. Okay. Now here I'm going to FOIL, right? And I think I can think about foiling, or I can just think about what foiling is actually having me do, which is saying take the first term in your first number, so that's the x here, and multiply it by both a and b. Okay, so to simplify this, I'd have ax plus bx, right? I multiplied x times a and x times b. And then multiply the second term, this negative y times a, and then times b. So I'll have negative ay minus a b. I'm sorry, that's the wrong, not ab, by. Right? And so this same idea can be applied in any situation. What you are doing when you're multiplying two groups of things is you're taking each thing from the first group and multiplying it by each thing in the second group. And then you're taking the next thing in your first group and multiplying it by each thing in that other group. And you're just going to keep doing that until you're out of things to multiply. Okay? And then you can collect all those like terms and simplify your expression. So hopefully that was a little more helpful. I don't want to give you too much help because you can do this on your own. So if that's helpful, good. Keep at it. Your goal is to actually prove the whole identity, and we'll talk about it a little bit at the beginning of class tomorrow.